Starting the lesson with a cheesy meme. Well, isn't that what all maths teachers do? Well, it's certainly what this one does, ish. As you can see here, volume at 16 is too low, 18 is too much, and 17 is an odd number. What volume do you possibly choose? In that situation, I don't know, I would seek therapy. It's way too complicated, but I don't know, maybe like me, I'd cruise down the road in my car, window open, stereo going, bit of doof, doof, doof. Does that not make life better, particularly after a hard day? Yep, sadly though, this lesson has nothing to do with volume in that sense, and everything to do with volume of prisms and cylinders. Hey guys from Internet Land, welcome. Thanks very much for watching. Hopefully you find this useful. If you haven't already, subscribe. Life would be fabulous, and it would help me make me feel so much better. Those of you who are cursed to be taught by me, then you can see there, those are the questions I want you to do, but not the enrichment question. Yes, if you want to have a go, then knock yourself out, but otherwise, just those questions. This is a continued video in terms of a measurement series that's tied very much to the Cambridge Essentials textbooks. And so, recapping, we've done a lot already to find surface areas of particular shapes. We've done prisms and cylinders, we've done pyramids and cones. Having done surface area for all those shapes, we're now going to look at the volumes. And we're going to start with prisms and cylinders again. Now, prisms and cylinders, I think, are flipping awesome because it's actually really simple. First things first, volume of a prism. You need to always know that volumes are always measured in units cubed. Now what I mean is they don't use the word units, but they've got to have cubes. And as I say here, the most common are kilometers, meters cubed, centimeters cubed, and millimeters cubed. These are the ones you're going to be using. Now with this, you're also going to need to make sure that in an exam, you write the units of volume. If, for example, I gave you this shape here, and I said it was 6, 4, and 8, then without rushing things, we would say that the volume would be 6 times 4 times 8, and we would write our answer in units cubed. We'd actually use the word units. Why? Because there are no units in the question. However, if I had told you that this was centimeters, centimeters, and centimeters, then I would do my answer in centimeters cubed. Why? Volume is three-dimensional. Bang the 3 on the top. Volumes for liquids are called capacities. They're worked in very much the same way, but what you need to know is they are measured in, and you notice that my spell checker here does not like any of these words. I do wonder why. They are measured in megaliters, kiloliters, or kiloliters, liters, and milliliters. And all of the units there are shown. So ml, kl, L, and ml. Milliliters, right. Do you remember in a previous lesson we talked about the idea of converting between measurements and areas? And if you remember, I told you to start with meters and go to centimeters and millimeters, because those are the ones we use the most, and I tend to write kilometers in there afterwards. There are 100 centimeters in a meter, there are 10 millimeters in a centimeter, and there are 1,000 meters in a kilometer. And again, we shouldn't really say kilometer, but let's not get too bogged down with that. That was for distance. When we had area, if you remember, kilometers squared to meters squared to centimeters squared to millimeters squared, that was area. Because we were making things bigger in 2 dimensions, we were going from a straight length to an area, which happens in 2 dimensions, we would then do times by 100 squared. We would do times by 10 squared. And we would do times 10 times 1,000 squared. Why squared? Because you are extending things. If that was your 1 meter by 1 meter, then the same would be 100 centimeters by 100 centimeters. That's got 100 times bigger, and that's got 100 times bigger. And so that's why we do times by 100 times by 100, which we can write easier as 100 squared. Same thing now works with cubic stuff, or volumes. So again, let's go from kilometers cubed to meters cubed, centimeters cubed to millimeters cubed. Okay, so if I now have 1 cubic meter of stuff, what that means is I have 1 meter by 1 meter by 1 meter. And when you buy lots of stuff for landscaping and all sorts of stuff, you'd actually buy cubic meters. So recently I've just done my gardening and I had to order topsoil, which came in cubic meters. So I had to actually sit there and do a calculation of how much mud I actually need in my garden. Random calculation to be doing, but thankfully being a maths teacher made life a lot easier. Now, if I now want to convert all of those into centimeters, for example, then that's now going to become 100, 100, and 100. What have we done? We've multiplied by 100, multiplied by 100, multiplied by 100. To go from 1 meter cubed, I've gone 1, I've multiplied by 100, multiplied by 100, and multiply 100 in 3 dimensions. I made it bigger in 3 dimensions, so I had to multiply it by 100, by 100, by 100. And again, so to go from meters cubed to centimeters cubed, I could actually write that as times 100 cubed. Now, how do we go from centimeters to millimeters? Normally, we times by 10. So with volume, I times by 10 cubed. And to go from kilometers to meters, I would times by 1,000 cubed. And when we're doing things the other way, we would actually divide by 10 cubed. We would divide by 100 cubed. And we would divide by 1,000 cubed, putting that in brackets as well. Really, really important. One of these things that you'd probably put in your notebook or you'd put in your summary book to help you remember these things. I don't know that you'd necessarily want to remember all this for an exam, but you'd want to have it on reference. I always try and prove it. I always use this one first for distance, then I use, the same information for either the volume or the area, and it works for me every single time. So, I don't know. Maybe you want to do it. Now, you need to do something like tattoo the following onto a body part. Now, actually don't. I'm joking. I do not understand why somebody would do this. It's actually real. This is actually somebody has put the quadratic equation on their neck. Either they are seriously doing that for a dare, or they love mathematics. But either way, please don't tattoo maths on you. No. What I'm trying to say is this is really, really important. To be able to go between volume and capacity, and remember capacity is done in terms of liquids, you need to know that 1 cubic centimeter is the same as 1 milliliter. Now, did you hear what I said there? I said cubic centimeter. And you're probably going to say, well, hold on a minute, doesn't that read centimeters cubed? Yes, but again, language in maths is there to trick you. Cubic centimeter and centimeter cubed, same thing. Volumes of prisms. What is a right prism? Can we have a wrong prism? Lol. Again, doesn't get much better than this. The definition is a right prism is a solid object with 2 parallel bases or ends that are identical and flat faces that are rectangles. Okay, an oblique prism, probably as I say there, is better for show. So there is an oblique. What do you notice? It's actually slanted. It's a prism that's effectively been pushed over. I could still put that through my bread making machine and I would still get individual and identical pieces because it's called a prism, but it's pushed over. So a right prism would actually just be something like this. That is the worst diagram I have ever drawn in my life. But imagine the point of it is that the base here and the top are directly atop of each other, all right? They are at right angles. So let's draw a right angle there to make sure that's it. All right, so here's a right prism. Yay! Let's make this slightly smaller so we can all fit it on one screen. Here's a right prism. Here's an example. It is a right rectangular prism, otherwise known as a cuboid. So, really, really important information. As I say here, the front of this shape, and it's always interesting to try and work out for a right rectangular prism, where is the front? And in fact, it doesn't matter. If I'd actually here shaded in this section, it wouldn't make any odds whatsoever. But this is called the cross section. Now, it doesn't mean that it's upset. It's a section that's upset. It's like, I'm not cross with you. It's just called the cross section. It has to be uniform throughout the shape. Now, in this situation, what we notice is if I was to slice all of my pieces going this way, then they would all be identical. So the cross section there is perfectly acceptable. Likewise here for a cuboid, if I was to cut this along all of these ways, then likewise they would all have the same front. They'd all have the same area. And the great thing with right rectangular prisms, and in fact lots and lots of prisms, is that we can use a formula that says the volume of a prism is given by the area of the cross section times by the length. And what it means by length is how far back it goes. So in this situation, it would be, as I've just drawn that arrow there. In this situation, it would be equivalent to the arrow I'm just drawing now. If you can remember that volume formula, you're going to have the best time ever with these questions, right? So example 2, find the cross section. Where is the cross section? Remember, it has to be uniform. You're looking at how would I put it in a bread machine to get equal slices and what would the front of it be? And in this situation, as I'm coloring in now, this here is the cross section. Why? Because if I slice this going this way, you'll notice that it'll actually end up with all shapes having this triangle. So the area of a cross section, because that cross section is a triangle, 12 and 9, how do we find the area of a triangle? It's base times height and halve it. Marvelous. So the area of the cross section will be given by a half times 9 times 12. And then, because my formula states volume is area of cross section times the length, what is the length? It's 18 centimeters. So putting that into my calculator will give me the volume of my whole shape. This is awesome. And it's true here with hexagonal prisms, different triangle prisms. So long as with the prism, you can color in which part of the shape will be uniform throughout. And generally speaking, the front and the back will be the same. And so that's the cross section. If you can find the area of the cross section, you can multiply it by how far back it goes, and you will always find the volume. Now, people say about these hexagonal prisms, how do you find the area of a hexagonal prism? Well, as I've drawn here, you can actually split a hexagon up into 6 triangles. 1, 2, 3, 4, 5, 6. And it just so happens that all of the triangles in a hexagon will be the same length. And so, if you can find the area of one of those triangles, 6, 6, and 6, for example, you can then go on to find the area of all 6 triangles. Now, sadly, in this situation, what you notice is they have not given you the height. So in this, you'd have to use some some Pythagoras theorem. You'd have to find the height of this to be able to help you then find the area. Or you can use Haversine's formula, which again is probably beyond the scope of this video, but there is a formula out there that given the 3 sides, you can actually find the area of a triangle. Maybe I'll do a video on that some other time. 4th example, and because it's really important, here is my cylinder. How do we find the volume? Well, again, remember the volume is given by area of cross section, and we can write that as area of xx, xs, multiplied by depth or length or whatever you want to call it. In this case, it would be height. So cross-sectional area, as it turns out for my shape here, look at the top and the bottom. They're both circles, which is awesome. So one of those is my cross-sectional area. Area of a circle is given by pi r squared. So that would tell me that the volume of this shape we're given by pi r squared times by the distance between the 2 circles, which in this case would be h. That formula there, as I've said, is really, really useful. It's used a lot for cylinders. Now, once again, this question came from the Cambridge Essential textbooks, and I am not trying to infringe copyright in any way, shape, or form. Composite solids, really, really important. Do you remember when we did surface area? So let's have the same idea as, remember when we did surface area, we had a cylinder on top of a cuboid, and we said, we needed to be very careful because you'd find the total surface area of the cylinder. You could find the total surface area of that, but you then needed to make sure that you took away the overlap. So you'd need to work out the area of the base, times it by 2 because it's there and there, and then take that away from your final answer. Well, the good news is, with volume, we don't have to care about overlap. Who cares? We just need to look at the idea that there are 2 shapes. One, which is the cylinder, hello, my old friend cylinder, we like you, and 1, which is the cuboid, as I say here. So, working out the volume of my cylinder. Volume is equal to pi r squared times height. We know the radius of the cylinder. Now again, math is a big fat trick. Where did I get 4 from? Well, we now know that this whole distance here is actually equal to the width of the cuboid. And because they've told me the width of that is 8 centimeters, that actually is my diameter. So how do we get radius to diameter? Well, radius is equal to the diameter divided by 2, hence the 4. And where did the 5 come from? Well, the distance between the two areas that look identical, so these two circles or the two cross sections, is equal to 5. And so I would go away and work that out. Now, my advice here, as I've said, is always leave your answers in terms of pi until the very, very, very end. Don't try and round answers now, because you'll start getting rounding errors. Cuboid, we know the area of a cuboid is given times base, times length, times height, or whatever. So because these little doubled lines mean that those distances are the same, we get 2 times 8 times 8, which is 128. And so my volume, my total volume, is given by 128, which came from my cuboid, plus 80 pi. Where did that come from? Again, it was 4 squared times 5 times pi. It is only now that on my calculator will I actually put that in, and I'll let it work out and round to 2 decimal places. I won't have rounding errors. Life will be really, really good for me. All right, so as is normal, again, please don't do that tattoo. In fact, don't do any tattoo. It's so... We've reached the end of the volume of prisms and cylinders. Thanks very much for watching. I, of course, as always, look forward to seeing you next time.
It's been so great having you watch this video that I'd like to see you again and again and again. Wow, we could make some amazing maths together. So, if you'd like to, and you'd like to be updated as to when I upload new videos, why not subscribe by clicking the button on the right? Otherwise, if you want to click and see another video created for this type of series, then click the video on the left. Alright, well, you have an awesome day, and I look forward to see you again.